All right, I guess we are both live now. Great. So welcome everybody to the last colloquium of this academic year. So Opti 595A students, you have one last chance to excel. And I'm very pleased to welcome Dr. Ivanka Palaszczynski back to Tucson. Yes. She's no stranger to the campus or the College of Optical Sciences since she took a bachelor's degree, master's degree, and PhD from the U of A in optical sciences. But she's coming to us today from the Aerospace Corporation in El Segundo, California, where she is the director and founder of the Integrated Sensor Design and Analysis Department at Aerospace. The department designs electro-optical payloads in a concurrent engineering platform, which we'll be hearing about today, that enables designers to model the effects of the space environment, including thermal and structural changes on optical performance. The department's also involved in CubeSat experiments and airborne remote sensing system pathfinders. She had a previous position at Aerospace Corporation as the Associate Director of the Integration and Testing for several Class A national space assets, and that's nothing to sneeze at. She has supported the Department of Defense and the National Reconnaissance Office in the development of novel optical materials and technologies for future large aperture systems, and she will not be able to tell us how large, unfortunately,
yes.
Although that would be very interesting to know. She's an expert on space qualification of new optical materials. She was the principal investigator for the materials on International Space Station experiment, MISSE 6 through 8, including work with some local folks here in Tucson. Prior to joining aerospace, Dr. Palaszczynski was a research scientist at Jackson & Toll Chartered Engineering, working in integration and testing of one-of-a-kind, high-risk experimental spacecraft for the U.S. Air Force. So welcome, Ivanka.
Well, thank you.
Thank you.
Thank you very much. Again, thank you, Dr. Hart, for inviting me, and I also want to thank WEO for suggesting me as a colloquium speaker. I'm really happy to be here to talk about taking optical design beyond just the basic designs. Optical engineering is more than the optical design that we're used to if you're an optical engineering student, and understanding all the complexities that are associated with actually building and developing an instrument for on-orbit operations. Success, I can work the computer. So today I will be covering a broad range of topics only to show the example of the breadth that's required in collaboration for optical engineers to work with other specialists to design these instruments. And so quite a few charts. I had warned Dr. Hart that I have 51 charts. Some will be more dense than others. They're more for reference if people are reading along as they're listening to me. So feel free to ask me questions throughout the presentation. So today I will be covering what it means to have EO space systems. What are those things that we're worried about as engineers in optical design? And then I'll go over the concurrent engineering environment and using something called STOP analysis, which is structural thermal optical performance. I'll go into CubeSat design of a system we're doing at Aerospace called AC-11, and I know people have heard that that's the new trend, and trying to do smaller satellites and that be able to test technologies earlier on to then bit them into Class A satellites. And then we'll also talk about airborne pathfinders. So in addition to using a CubeSat platform, one can learn a lot about future technology and interesting optical advances using airborne systems, and we'll go over some of those principles associated with that. And then finally, based on what the request was from Dr. Hart as part of the colloquium to expand what one could do in a career, I'm going to talk a little bit about what it's like to be part of a federally funded research and development center. It's not always a common term people know about or a possible career opportunity, so I wanted to speak a little bit about that at the end. So in terms of the role of an engineer, an optical engineer in EO systems, it's changing a little bit. So when you leave school and you go forward into the real world, there's a lot you have to worry about when it comes to a space system. It's a little bit more complicated, more things to be concerned about. So as you see here, we have to work more interdisciplinary ways. It's more than just optical design. We have to look at integrating and testing a system for space, and I'll go into what that is all about. And also, the space optical system design process itself has become less stovepiped. Traditionally, early on, when space became one of the things we were reaching for in the early 60s, things were relatively stovepiped. So an optical engineer would design something, pass it to the mechanical engineer, and then that would go on to thermal analysis. But now, things are becoming more collaborative, and the responsibilities are blending a little bit more. So optical designers need to see the big picture to know that the choices we're making for a design will not negatively impact other areas of a system. So again, part of the thing that I look for when I work with a team is, can that optical engineer be knowledgeable in other disciplines, at least know what not to do? Maybe not necessarily how to solve the problem, but some of those red flags so we can successfully make good choices for the other design engineers on our team. So space. We hear about it, and we don't necessarily, if we don't work it all the time, we don't know what the concerns are. So as you see here, we see beautiful radiation belts, and lots of great things happen up there to our systems. So we need to, for example, worry about the longevity of the materials we choose. Is there degradation in the performance? So those are the things that we consider as designers. But in addition, it's once we're up there, but we have to get there first. So the launch environment can be very detrimental to systems. So when we are on Earth, we test those systems in integration and testing, and I'll go into that a little bit, where we model the vibration, acoustics, and shock environments that these systems are going to experience before going on orbit. Now, radiation, that's the part that causes some problems for our optics, especially if there's darkening, or if the materials that are enveloping the spacecraft start degrading, then the thermal effects could start affecting performance as well. So the thermodynamic environment, as this particular satellite or other object is going through orbit, you're going to see a lot of temperature cycling. And so then, depending on when imaging is taking place or what the mission of this particular system is, you're going to have to be able to maintain that optical performance in this dynamic environment. So that's where part of this concurrent engineering helps to resolve some of those challenges of working with various disciplines. So again, the selection of materials that are radiation tolerant and the shielding will enable us to design optical systems that have a longer lifetime. And again, the whole point here is that space just adds additional constraints on what we need to do. So traditional systems engineering is an aspect of pretty much everybody outside of industry. We have this classic systems engineering V, which tells you about the life cycle of a system. So we'll be going through on the left side, looking at requirements, understanding what is the goal of our system, and then as we go up, the upper part of the V is where we're starting to build and verify that what we designed will actually perform on orbit. So this is what we would term the systems engineering V. And again, those things ensure that the original job that was led by the Air Force or another customer will actually meet the end user performance needs. And to be able to work this V effectively, most teams require multiple disciplines, and we draw from, in most industries, a matrix organization where we're able to pull teams from different departments to work together. And because of this, the requirements in general have to be across the system, and sometimes they are stovepiped, but as things are trending now, we're really trying to make sure that the requirements are more complementary to each other. And again, we verify that successful flow down of requirements in integration and testing. So now there's something new happening. It's a trend that's occurring within the aerospace industry, not Aerospace Corporation only, but the industry itself. And this is actually a very positive change where it is now becoming concurrent engineering. And here we look at the mission performance, and at the same time we're able to model on a platform what all of the different parameters from the different disciplines working together. So we have engineers working in their very familiar softwares, for example, Code 5 and Nastran, Thermal Desktop, passing parameters on a platform that, in our case, is a software called Comet. There are many others commercially available and also ones that people develop in-house. And this allows us to share this information and evaluate that performance before anything even goes into testing. And this is really only now possible because of computing power and software advancements. So these virtual models become an important tool because in previous times, what we would have is we'd have an engineering model that we would build and have some critical components and then the full flight model. And if there were problems in testing, one would only be able to use this engineering model, which had approximations of performance or maybe not the same components but close enough. And we would have to do anomaly resolution with sort of the not the perfect system that we're actually putting on orbit or as it's currently on test. by having these virtual models, you have the identical component outline and the layout of the CAD and all of those performance in this concurrent engineering environment where you're able to actually simulate what you're seeing in a test or even on orbit when there's a problem. So it's a really great opportunity to know your system really well and be able to evaluate it. So this is a great strength because we're able to decipher problems much faster. And as I said, as an industry as a whole, we're seeing a lot of contractors moving towards this type of design. So in terms of integration and test that I'd mentioned before, the point of it is to verify and simulate the environment that this particular system would see through the launch to on-orbit performance. And so we have thermal ovens to bake out contaminants prior to integration of these particular components. We also are able to do optical testing pre- and post-environments, and depending on the value of the asset, we're sometimes able to do this type of testing, optical evaluation, within a thermal vacuum chamber. So but the goal of all of this is to also exercise all the critical deployments of a system. So as we list here, solar arrays, optical covers, telescope booms, all of these things are evaluated to make sure that they do perform properly. And of course, the thermal vacuum environment creates that ability to test any outgassing or any kind of darkening that might happen on an optical system. And vibration tables, of course, simulate the launch environment. And shock, which is critical also, is that separation from the launch vehicle. And the whole goal here is the INT process should be catching those problems before we're on orbit. So now I'll talk a little bit more about this structural thermal optical performance. So stop modeling, again, as I mentioned, is more of the as-built, detailed representation of the hardware. And the goal is to really look at that optical performance change due to effects on the structure and the thermal components. And again, this opportunity is for engineers to work together in the same room and pass information not just through the databases that exist, but also be able to be close by to discuss the issues and find ways to make sure that those requirements actually close. So what's really great about this is that we're actually learning from each other, and so our optical experts can learn more about the mechanical concerns. So the next time we design something, we're a little bit smarter and we're able to be more effective in how we create our designs. And then one benefit also about this is that we're able to follow a sensor throughout its development. We're able to look at, evaluate a quick schematic and a quick design. We're able to analyze and validate any existing design changes. And then, of course, predict any on-orbit performance problems. And once something is on orbit, we're able to even assist in anomaly resolution. So again, the stop modeling is something that is able to support a system throughout its lifetime. So lots of stuff here. But again, it's an iterative model here. And again, as I mentioned, people would work in a Code 5 or Thermal Desktop, and we create meshes and ways to represent and put onto this CAD, for example, the information that's relevant for the system performance. And as we're growing this model and as the design changes occur, we're able to augment the model and improve it. And then we just go through and are able to do predictions on the optical performance. So the purpose of stop analysis for the Aerospace Corporation is a little bit different than maybe at a standard contractor. And the reason for this is that our job as a federally funded research and development center is to be the technical advisor to the particular customer paying for the work. So our job is to actually be able to provide feedback on the status of a contract, areas of risk. So we perform independent analysis of a contractor design. We support preliminary design reviews and critical design reviews where we provide feedback on what is necessary to change so that the design closes and meets end user performance requirements. And then also, as things are developing at a contractor, from a CDR to actually cutting metal and creating the optical component, we're able to support factory testing. And so, again, part of that is the anomaly resolution portion. So this is a life cycle of a system, and I was just showing here where we have pre-conceptual design phase, a preliminary design, and then final design and build and test, we have actually supported in all the blue areas the flight anomaly resolution we have not, and it's actually a good thing right now because that was based on a lens focus anomaly resolution. I'll talk about that in a few charts, where we came up with an anomaly resolution plan, and it actually is working successfully. So it's good. But we would be able, if there were other complications associated with this particular system, we would be able to assist in figuring out how we could improve the performance. So again, this is a virtual flight model, which is what stop analysis allows us to have. So this is the first example of where we were doing a quick analysis of just a design to see what area of risk would we be identifying. What could be the biggest problem for this particular telescope? And as we were going through, we noticed that there was a need for a sunshade based on the thermal performance, and that there was expansion from the titanium mounting ring and the primary mirror. So we were able to at least locate, when this person was coming up with this design, that the highest area of risk was in that particular region. So we were able, and this was a much less complicated system than we normally model, but again, it was an initial design, and we were able to tell the customer, you know, this is where we need to look, and we need to redesign some things. So again, it was a short duration study, but it really provided a high value amount of information that may not have been found in a very stovepiped process for designing an optical system. Now, the next one is a little bit more complicated because that is actually a flight system, and it was in thermal vacuum. And what occurred was that the performance, there was a large gradient across the system, and it was not expected. And what we were doing is we took the models that we had and we were simulating the results that were happening in thermal vacuum. So we could set up the conditions of what would result in such a thermal distribution. So it turned out that the heater design was not implemented properly on this particular sensor, and it was too small to be able to heat equally the large part, the front end of the system, and the back end. But we were able to come up with a thermal control loop that would upload thermal values to be able to help control the system. And so, therefore, the good news was they were able to continue and meet their schedule, because unfortunately, in the real world, we're not always able to do the ideal solution. We may have a launch date and we have to go, so we have to come up with something that's workable. And so we were able to do that and have them meet schedule. They didn't have to pull out a thermal vacuum, which is a very expensive process, especially with a standing army of engineers. So we were able to find that solution, but at the same time, we were able to help improve the next generation of the sensor. So again, everything being iterative in engineering, we were able to make an impact on the immediate system and improve future systems. So this was one of our big show-stopping moments. And we do have other examples, but they're on other topics, so we will not go over those. Next, I would like to talk a little bit about CubeSats. CubeSats are now, as you know, becoming more popular. They're a much less expensive way to access space. They also provide a great platform for university students to be able to provide experiments and have the ability to design a system that operates in space. Another thing is that actually a lot of customers are considering breaking down the Class A satellites into smaller ones so that we're able to break down individual performance requirements into sub-satellites. It also helps because we could do redundancy a little bit easier. If one part went out, we could send up another smaller satellite faster, because the timeline for a Class A satellite can be up to a decade from the design to launch. So that's quite a while. And sometimes by the time you launch it, a lot of the components have already evolved further, but it's too late to include them in a next design or in that moment. So CubeSats allow us to put the latest technology into space, verify how it works, and then include them into future systems. So they're able to support a disaggregation of a Class A satellite system, but also support improvements of technology for future Class A satellites. So I sort of went over that here. And also, the benefit of a CubeSat is it is standardized. So they are standardized in U units. So as you see here, they're 10 centimeter by 10 centimeter by 10 centimeter. And it allows people to be able to purchase inexpensive buses to support such systems. You can buy them online, or you can buy them from vendors that sell CubeSat launches. And so at the same time, at Aerospace, we designed our own. And so we're able to reuse that bus structure to be able to check out new technologies. So again, fielding of CubeSats is really to perform some of those missions traditionally executed by Class A, but it again allows us to do things faster and less expensively. So in terms of the heritage of the Aerospace Corporation, what you see here is very challenging to see some of the little dots, but we have 6 CubeSats that are currently on orbit. They have, one is an imaging camera, and then it became the same, but it was a larger form factor. So again, basic imaging, fisheye, medium field of view. And then we also had 2 other CubeSats, smaller form factor, carrying dosimeters. Again, we were just checking out some components. So we're trying to understand what those possibilities are to include new technology, again, in terms of dosimeters, and then just trying to understand what we can see from space on a small, inexpensive CubeSat. So I would like to specifically talk about AeroCube 11. And this is actually Aerospace's first optical payload on a CubeSat. So we've done others, as you've seen, but they haven't been optical payloads we've designed. But this is the first one. And the objective here is to collect data similar to Landsat OLI in a LEO environment. So we had a spare OLI filter, and we were able to take advantage of that resource. And so we provided some push broom collector capability, and then these particular statistics that you see here, and basically the requirements. Now, the idea here is that we were trying to show that we'd be able to design within the form factor and then collect the satellite data so we could compare it to some databases that NASA has available. So what you see here in these 2 pieces is that in our case, the bus, the optical portion, is only in the front half, but the bus is in 2 pieces to make it easier for assembly and wiring. So we have the 2 solar arrays and then additional solar power here. But again, it's just this configuration is only for simplicity of assembly of the wiring as well as the electronics. So part of an optical engineer is to also be efficient with cost. And so one of the considerations we had was, well, if we're using a CubeSat, and it's very common to use, off-the-shelf components. So these are commercial off-the-shelf called COTS. And so we wanted to investigate that. So we went ahead and found a lens system that we thought could possibly work. And so we took an X-ray of it and wanted to see, can we use this for space? As you see, there's very complex movements, and there are doublets. But unfortunately, we were not able to use this system because there was grease in there to make it easier for the mechanisms to move. And there was also a doublet with basically an adhesive that would more than likely outgas. So we could not take those risks on the particular design because we don't know what that would be. Even if we cleaned the mechanisms, the probability of us getting it all right was very low. So we decided the best way was for us to design our own custom lens. So again, as a designer, though, there are many times where using commercial off-the-shelf systems are perfectly adequate. But in our case, after doing further investigation, this was not the case. So here we have our custom AC-11 payload. We, of course, had to work to minimize and fit within the 2U format, just based on the amount of space we had. So we were able to design our custom telescope to operate over the appropriate wavelengths. And then, again, we made sure that we did not require any grease or any bonding to make the design work. So we also wanted to make sure it was inexpensive, since this is a CubeSat and it's just supposed to be quick to do. We wanted to make sure we only use spherical surfaces, so manufacturing and costs would not be an issue. So this is the design that was produced. Then we also, of course, had to make sure that the telescope met optical performance. So we had a requirement for, and we actually ended up having within our performance 55% margin. So we were happy to see that. And of course, even though you have margin, once you build, things happen. There's different requirements. There's tolerancing that as much as you design it in doesn't always necessarily equate to when you actually build it, because when people make the lenses, some things may not perfectly align. So we ended up having 2.5 times margin, and that's still very good. So we were very happy with that. And then our MTF was perfectly within requirements as well. So again, the important thing to think about is margin is your friend, because if you don't have it, you just know that errors and will just continually stack up and it'll eat into your margin. So it was actually very wise for my designer to actually build it with more than we needed, knowing full well it would probably drop. So in terms of the optical payload mechanical mounting, so the mechanical part of this is the fact that we have to be able to put everything together in the 2U space. So we have to be very effective in how we assemble, so it's not difficult. We also have to make sure that it carries enough of the information and the structural integrity for when we launch. So we were able to make sure that it met the thermal and vibrational requirements. And the person from my department that was the optical payload lead, he had to spend quite a bit of time working with the mechanical people and the thermal people on the CubeSat side to make sure he understood what was feasible and what would be necessary so that we would be able to meet the performance. And as you see here, we had to have a radiator so that we would be able to maintain that thermal performance and therefore our optical performance on orbit. So we also had to have that heat sink. We also, the spectral filter itself, we had to have enough of an adjustment so we would be able to keep things in focus and be able to image properly. So as we said, we designed it so we were able to survive vibration and the temperature changes. Now, this is quite an eye chart, but the only intent of this is to mention that there's a lot of work that goes into verifying requirements. It's one thing to have them, but how do you go forth in a true systems engineering process and make sure that you have done the due diligence to meet the requirements? So what you see here is a list of all the requirements, the description, and what one needs to do to verify or to say that you did meet them. Some things are verified by analysis, others by test, and others by inspection. And so it's a very painful process to do the first time, but it is truly the only way to keep track of all of the requirements to make sure you meet your payload needs. So this is just an example of an eye chart of what is required in the systems engineering process. And this is just for a CubeSat. So imagine what goes on a much larger system. Now, integration and testing. So this is for the flight payload unit only. There is other testing that occurs at the bus level. So when we have a large satellite, we obviously have different missions. One satellite can do multiple things. So we may have an imaging mission, we may have a sounding mission on a large spacecraft, but each of those individual instruments have to go through the INT process. And then once those are integrated, then the bus itself, before it has payloads integrated, goes through the integration and test process. And then when the entire assembly, the whole space vehicle, is integrated, it too goes through environments. And of course, depending on the cost of the program and the risk that the customer is willing to accept, there will be either a lot of testing or a reduction. What you see here is this testing campaign is less stringent because it's a CubeSat. The cost and the timeline that we have, we were willing to accept a little bit more risk on the payload because it's a demonstrator, and then we would be able to learn from it. So we were able to create testing that's a lot shorter on the payload. So we would look at testing the telescope assembly, and then be able to look at the focus mechanism, because we obviously have to maintain focus while we're in a thermally changing environment on orbit. And we were doing mechanism testing. And then we obviously want to check all of the mounts. And then from there, we would integrate everything, and we would be doing a payload thermal vacuum testing. And afterwards, we take that out, and we're doing calibration on the system to make sure that what we did beforehand still matches what we're seeing now. And then, of course, we would do a vehicle testing integration campaign once that payload is delivered to the bus team. Of course, this bus is very small, but it is a big moment when we deliver a payload fully tested to the bus team. So again, INT ensures the flight worthiness of the AC-11 program. Now again, the great thing about CubeSats is it does provide students the opportunity to understand what an integration and testing campaign entails. But again, the same principles follow for larger satellites that can accept only a small amount of risk. So I wanted to show some data from the vibration testing. And what you see here is the control. And of course, we kind of went above in our vibration test. This is only for the focus mechanism. The telescope was also evaluated for vibration, but this is the data that I had available at the time. And what you see here is we're performing it to NASA standards. So in addition to having a very specific integration and test plan, you have to work against standards. So the Air Force has testing standards and NASA has testing standards. And for this case, we chose the NASA GEVS program. And so these are based on historical records of the types of tests that were required based on 1960s launch vehicle flights. And again, the philosophy here is test as you fly, which means you really want to replicate the expected on-orbit or launch environment on your parts to ensure that they will survive. And then the setup has the control and payload accelerometers on each axis. And then we made sure that we looked at the data and that the payload did survive vibration testing and pass the post-test accuracy check. So again, we want to simulate the environments and verify pre- and post-performance. Now, in terms of CONOPS, so as much as we like to worry about what we're doing and when we're launching, as optical designers, we also have to think about how are we going to use this system on the mission. So we have to make sure that we have the appropriate, for example, reaction wheels when we are trying to do a mission. Here we see our particular satellite at the orbit it's going to be operating. And as you notice, there are some maneuvers that are occurring that rotate this particular spacecraft. And that's because we need to keep the optical bore sight facing the Earth. Because we do enjoy stars, but our mission is to look at the Earth. So one of the things we had to make sure is that our reaction wheels were appropriate and that we set up the CONOPS, because we don't just send something into space and hope it works well. We do have to plan everything out, and planning includes all the data you're going to transfer down, and I'll talk about that in the next slide. But again, here, as we're determining our orbits, this provides feedback to our thermal team. And that allows us to know exactly what we need to have on our materials to ensure that the performance is maintained. So again, the takeaway here is that we want to make sure we point the optical bore sight at the Earth. We want to keep our focal plane array cool, otherwise the performance degrades. And then also, we want to make sure our spacecraft is powered so that our solar rays face the sun as much as possible. So, yes, very complicated. Yes, I know. But this is what it takes to be able to understand when we're going to be downloading the imagery we collect or when we do image collects. So again, we would have some places where we always want to be able to check our position. So we, in some cases, are simply collecting the information from the GPS satellite system to know where we are. And in our case, we're going to do 7 collects. So actually 3 collects, and then we're going to have communication with our ground stations. So this is just a representation of what goes into a flight plan. There are many documents that are generated to show when we can download, because we have only so much time that we can download a certain amount of information during a pass, because we cannot see the ground station for more than several minutes. And so then you have to be able to download all of that information. So we have the timeline here, the number of passes that we see, what we're trying to do with the space segment, and in the ground segment, where are we trying to do those downlinks, whether it's to make sure that we have the correct geolocation or whether we're trying to download the data we've collected. So again, it's a lot of coordination. So as you see, the more you get to the broader perspective of the mission, the larger the team becomes that you work with. So instead of just thinking, oh, I'm only working on my payload team, now I got to work with the launch vehicle provider. I now need to look at the ground systems. Do I have, sometimes, you have to make sure you have the right electronics to communicate with the ground system, the right protocols. And if you miss that step, you may be orbiting, but you may not be able to get your data down as efficiently. So those are some of the things you have to think of. And as systems engineers, they are the ones that look at the whole picture and decide where one does a collect, where one downloads data. So it's a very big problem to step away from just the optical design of the telescope, which we certainly want done well, to actually supporting the entire mission and the objective. So here I just have a quick little map of the 3 ground stations that we have, actually 4, there you go, Hawaii, there you go, that we have that collect, and we also have mission control right in our facility at Aerospace. It's at the Physical Sciences Laboratory portion, so we have a mission control there, so it's kind of fun to be able to check out what's going on. And again, we want to be geographically separated so that we have other opportunities to download our data. Are there any questions? Chatting? Okay. All right, we're halfway through. Hang in there. All right, so now I will talk about MACO, which is a long-wave infrared hyperspectral imaging system. This is a system that my subdivision had supported. This was a while back, so it's prior to my arrival, but it does have the same concepts of what my team is doing now as we're supporting airborne missions on polarimetry. I didn't have the data available to present that, but I wanted to cover the information on the MACO. So why are airborne systems of interest? So for our case, in general, it's great to collect airborne data when we're looking at missions, for example, where fires are, all those kinds of things, meteorological surveys. But in our case, the reason we're also very interested in airborne systems is that it actually emulates the low Earth orbit imagery where a lot of our sensors reside for our primary customers. So the reason it's good is the fact that it is able to basically simulate the GSD or the ground sample distance using the same focal plane and also have a similar velocity in terms of how we would be collecting the data from a satellite system. So this particular elevation of about 11,000 feet and the speed of a Twin Otter allows us to be able to collect this data. So that is the reason that we do favor the airborne system. In addition, as we're developing technology that's cutting edge and we're not quite ready to insert it into a Class A satellite, it allows us to do testing and bring the system back. So we can do some faster design work, take on a little bit more risk because the system does come back and we can make upgrades. So again, the more risk you can take on, the faster you integrate technology, the faster you can try something out. But once it's in space, it becomes a little bit more complicated. So that is the reason we also like to do airborne systems. So why do we want hyperspectral sensors? Well, they are very useful in imaging and getting information about gaseous emissions from compact sources. So this allows us to look at industrial urban environments, see what's going on. So in addition to helping and developing things for imaging for military missions, this is a great opportunity to help with environments. So one of our other systems helped when 9/11 occurred. We had some flights and evaluating what was happening from the 9/11 towers. So again, we are able to do something for the environment. Again, the survey of fugitive emissions, you're able to provide information to first responders, and you're able to inform which communities need to be evacuated. So it really does help out in that regard. And then again, it helps reduce the liability of exposure. So again, when we start doing these types of missions, we start really partnering with an even broader community because you're looking at not only the scientific community, but the first responders, political situations in the cities and states, and how can we help them. So it really becomes a much larger, complex problem. At that point, of course, the imager is formed, but then how do we manage our resources so we're able to help out? So I would like to talk a little bit more about MACO. So it is a whisk broom scanner. And again, that means that the sensor actually collects information by basically side to side, whisking back and forth. And it was built in 2008, but it was flown in 2010. And this was our original CBAS, was our original system. And then based on development of new focal planes and the availability of technology, we're able to really expand how much our system is able to correct and collect information. So here we see the instrument itself. This is MACO. And you see the cross-track signal, and the slit itself is being moved back and forth as the system is flying. So we're able to do a large area coverage. And again, the good thing is that this is high sensitivity mode. We're able to have noise reduction because we're using longer integration time. So this was definitely in a span of a few years, we're making significant impact to the way we're collecting the data. So in terms of, back to the optical designer, how does it begin and what do we worry about? So as in most cases, we start out with a schematic layout and somebody says, oh, I'd like to be able to do this and I'd like to image this particular place and have these characteristics. So we had a schematic and we wanted to make sure, because of the type of imaging we're doing, which is in the long wave, we need to be having a cryogenic environment. So we had a cryostat here, and we were making sure that this particular area is able to maintain the cold temperature required for optimal focal plane performance. And we had a cryostat window, and we wanted to make sure that this was a pupil point where it was basically telecentric, so we would then be able to have any type of afocal telescope here and image and test the system. So from here, from this very simple request, we generated this larger cryogenic optical assembly. And what was the goal was to be able to figure out a way to, because we have a focal plane and we have to be able to image that all through the optical system, we designed a Dyson spectrometer. And the Dyson is good because it provides high throughput and low distortion in a compact configuration. And therefore, it was also suitable for the infrared applications. Now, modifications were made to the traditional Dyson because it is a plano convex, because we wanted to make sure that we were able to move the focal plane back enough, the slit back enough, so we could actually put a focal plane there. So we didn't want it right against the zinc selenide object. We wanted to have a little bit of a distance for mechanical engineering to be able to place the focal plane within the system. So we had to modify the Dyson a little bit, but again, the cryogenic assembly was required so that we could do that long wave IR sensing. So again, we have to take advantage, and the reason also this was now possible is that in the 60s, it was not possible to have such a large amount of zinc selenide, and focal planes weren't available at that time, right? So it's amazing how advances in technology really help push what a designer can do with their lens design code. So again, technology matching and then pushing the optical designer to be able to do more. So here is, again, another end-to-end layout with the afocal telescope, and again, some spot diagrams. So again, the whole goal is that when you design a Dyson, you'd say, great, everything falls right on the back of that lens. But because we actually have to build a system that has a focal plane, is cooled, we now have to change a little bit about the Dyson and then change the fact that we need that extra room to put a detector. So here is the as-rendered SolidWorks and the cryogenic assembly itself. And so again, working hand in hand with the mechanical engineers and the optomechanical experts, we're able to create this design. Now, one might say, why is that so shiny? You know, if it's supposed to be able to take care of it. Well, in the long wave, this coating, iridized aluminum, appears black. So it would not be interfering and would not have all those straight light issues. So again, a hand-in-hand team here, the optical designer and the optical mechanical engineer make it possible. And this is actually part of the cooling, so all these holes and then this plate structure itself to help with the cooling of the system. So again, as designed and then as implemented. And so you see here a lot of components. Also, because we have this mechanical motion, we had to perform clearance to verify that as this mirror is scanning, that it doesn't hit any of the rails on this particular cart. And just make sure that and the reason is, why are these rails important? Well, we match these rails to the rails that will be on the aircraft, so that when we put this system in, we don't have any problems there. So we, again, simulated the cart and made sure that it was the same distance. We took a Twin Otter, and I'll talk about this plane a little bit, and we modified it so we could actually put a payload in. We took some seats out, and then we have a payload stand. And so this, in the lab, simulates it to make sure that we can do all the required testing before we implement it into the airplane and might have collection challenges. So again, we also have an inertial stabilized mount, and this is the scan mirror that we're checking to make sure that we don't have any issues with clearance. Again, so this is a collaboration between optical, mechanical, and electrical engineers so that we can go and collect that flight data. So this is the installation of the Mako into the actual plane. And again, the track of the cart matches the seat rails so that we're able to install that very quickly. And why is that important too is airplane hours are expensive, pilot hours are expensive, and we really don't want to waste too much time integrating the system because we want to be up in the air collecting data. So we want to make sure that we're as efficient as possible with daylight and our staff because these are really long days. To do a collect throughout the day, I participated in one a couple of years ago, and it's an early morning. You go and you make sure the plane is ready, and you do the plane checkout, and then this instrument's in, and then you go fly around. We were flying around the LA area, and it just takes time, and you want to make sure you don't have bad weather. So all of those things, we try to be as efficient as possible with the installation so we can focus on the science. So another busy eye chart, but again, showing that as much as we love the optical design, we love the software engineers even more, because they're the ones that allow us to take the data and make sure it's collected properly when we're on the airplane. There are a couple things with this particular software collect, is that we also have to provide the flight plan to the airplane pilot. So we tell them this is what we want to do, but we also have to put that into the computer system. So we have a flight plan, which I'll show in the next chart. And then at the same time, we have to make sure that as we're traveling and we're collecting the data, that everything works well so that we have the data, we store it properly, we're putting it into additional disks and additional space because we're collecting a lot of information over a course of a 4-hour flight. So again, all of this has to work together, and we have to be managing the stored information. Make sure we're also maintaining the line of sight, because when we have a flight plan, we're looking for something in particular with the data we're collecting. So we want to make sure that we are on that flight plan, we are getting the data, and that it's also properly registered with where we're looking. So we need to know where we're looking in addition to just collecting it. So this is the example of the flight plan. This is what we wanted to collect, and this is the flight path and how, again, we're whisking and collecting data. So we're coordinating with the pilot and the instrument operators to make sure we get that high data quality collect. Again, the Mako system uses the Otter command system, and then the pilot is directed by the Otter program where to fly. And again, it was georeferenced right here with other data collected, because the way hyperspectral image data looks, if you were to look at it, you're kind of like, what am I seeing? So we georeference this data so it's easier for an analyst to review it and understand what's happening. So here's an example of some fugitive ammonia from a gas-fired power plant. And so again, we're able to see the source here. And this was only 2.3 minutes of collection time, but there's a lot of information here. And of course, we've overlaid it over the area we were evaluating. And if you lived in the LA area, you could kind of recognize where this is. It's kind of near aerospace and by the coastline here. And then there are also some other sources that are identified. So again, data analysts, once they get this data, they now do a lot of processing on it to extract critical information. So it's amazing how it's a very large group of people. For the analysts, they're excited to get this, but they maybe don't even realize how much work got into even getting this data to them. And then this is the last part of the Mako here. This is the San Andreas fault. And what is amazing with hyperspectral imaging is that you're able to look at mineral content. And so we are able to actually understand where the fault line moves and where changes in rock the connection of the rocks where it changes. So you're actually able to map the fault line and then monitor that over time. So again, this is another way that we're helping, not maybe a first responder, obviously, but somebody who's really sitting and trying to understand what's going on at the San Andreas fault. We are able to understand the changes over time. So this is my last chart before I go into the portion on aerospace. So I was wondering if anybody had any questions before we moved on to that. Yes? Let's see. Let me sorry, I want to go back to that. So don't want to say it wrong. Right there. So let's see. So, yep, 44 nanometers, spectral resolution, 128 channels. So, yeah, so it's a pretty good system. We're now working on some polarimeters because that's also going to add additional information. So we're always trying to data mine more information and use technology as it's coming up and seeing new ways to apply it. So, okay. Yeah. Yes?
What's the effect of atmosphere versus no atmosphere?
Oh, sure, right, exactly. Because there are obviously, the good news of working in the long wave is that you're not as affected because of the water content. So there's obviously the water is a problem, so we try to work in other bands, but it can block some of our imaging depending on the wave band. So that if you have a lot of cloud cover, that obviously can be a problem, but in other wave bands, it doesn't really matter. If you're doing like a radar collect, that's great. You can see through clouds. So that's not a problem. So it really depends. So we do have to sometimes watch out for weather. Yeah.
Different question, sir. How about the index of refraction of air versus the index of refraction of vacuum? Does that have any effect on the whole system around?
That's true. That's a good point. I mean, that we do account for that a little bit, especially also not only the vacuum, but the fact that it's going to be thermally changing more on orbit. So we do account for that when we do, for example, the concurrent engineering portion. We do have to account for that because we try to simulate what is going on with the changes. So we try to make things that are more, stable over the temperature range we're interested in performing. And that's also why we also use heaters. So for some of our systems, we will actively heat the optical area so that, or cool it depending on what's going on, but we really try to maintain it. And in general, with the exception of like the large optics that are out front, right, they will be very, we try to do a lot of shielding around there as well. So we'll do baffles out front so that they aren't exposed as much, even though obviously they're the first things out there. So it really depends on how much we can do the thermal control. If there's some instruments that are more tucked into the spacecraft, that's a little bit easier to do. But when you've got a primary that's quite large, then we try to do a lot of sun shielding if that's necessary. Or the pointing itself will also accommodate, and also the CONOPS. So we won't be maybe imaging at a certain point so that we can maintain optimal performance. So we can use different parts of this optical, collection to maintain the thermal performance. So, anybody else? Okay. All right. So we'll skip ahead. All right, so I want to talk a little bit about FFRDC. So that's a federally funded research and development center. So I want to talk a little bit about what it's like to be working in that environment versus at a contractor. So the Aerospace Corporation operates a federally funded research and development center. So we provide engineering and acquisition management support. You're like, what is acquisition management support? Well, that is all the work that is required when we build a spacecraft or another space asset where the government is actually purchasing a product from a contractor, and then they have to be able to execute that contract and deliver on what they've paid for. So that is what we are supporting when it talks about acquisition management. And then also we do objective technical analyses and assessments. And so because we are not connected to the contractor, we can do that independent analysis and make sure that they are going to meet their requirements, they're using the best products, or their testing will be on time. So those are the things that we are responsible for. And we also do end-to-end involvement in space systems. So we do everything from, example, initial designs for systems that are going to be built. So we will help the government put together a request for proposal. So if we know there's some up-and-coming technology that we feel is important to be inserted in a future system, we can help show the government how it's possible to put it in, and then the government will let out a contract, and then the contractors will bid on that, get selected, and start performing on that contract. So that's one end. And then we also do support of launch once the system is built, do support of launch and on-orbit operations. So we really follow through from beginning to end of a spacecraft. And also, because we have been around since 1960, and we have a lot of information on the historical work that has been done in space by the government. And so we are the national repository for that information. So we have databases that contain that information. We also tend to have people stay at aerospace quite a while. So it's a great way to learn and mentor from people who actually designed some of the systems that we're currently working on or working to improve. And so that's another role that we maintain. So in terms of a way to think about us is we're sort of the unbiased technical conscience for national security space. And so we have this cross-disciplinary network of experts, as I've talked about throughout the presentation. And so we provide objective advice, and we help with R&D activities. Again, our goal is to work in the national interest. We are a nonprofit organization, so we do not have to worry about answering to a board of directors. So our job is to do the right technical thing. So we are able to provide the customer, for example, if something is not getting done on time, we can at least provide solutions of what to do to improve that. Or if there's a problem with a spacecraft, we can provide advice on the technical changes that need to be made. And then the government chooses which way to go. But we aren't biased by schedule, by what a board of directors would say to us. We are just doing the right technical thing. So we provide that independent, objective advice. So it is a unique role in the space community. And again, the other benefit, because we are independent, we do have purview to what is going on in the aerospace industry. We have unrestricted access to innovative, proprietary, state-of-the-art technologies. We have NDAs, of course, with the corporations that we have oversight. But again, and the key is to have mission success. And because of that, I think it's a great place to work because you're able to learn from what's happening across the industry. You're not just able to do one type of solution. You're able to see all types of solutions, and so it gives you a broader perspective. And so therefore, we have this think tank culture where we have highly educated and very collaborative technical staff. And we have internal research opportunities. And then also we allow people to kind of chart their career and decide whether they want to be very specialized or very diverse. So if somebody wants to specialize in one area and be in there their entire career, that's welcome. We have such experts, and it's wonderful when we have an anomaly and they know exactly what's wrong. And then we also have people that are more broad and perform more of that systems engineering role. So again, all variety of types of scientific contributions within aerospace. So to give you a little bit about the numbers, this is FY16. So we had $942 million worth of work, and of that, 50% was military, 35% was Intel Space, and then 11% is a civil systems group. Again, that type of work is more work we do for NASA and other civil organizations. So we are working to expand that particular portion. We have about 3,700 employees, and 2,500 of those are technical staff. And we have quite a large amount of laboratory space. And we have several major locations that have on-site laboratories. The largest ones are in El Segundo. And then these are all ready to help with anomaly resolution on orbit and other technical challenges that come up. So here are general locations. So we have El Segundo, where we have 2,500 employees. Chantilly is 587, and then 87. You're like, well, that doesn't add up. Well, because we do have smaller offices that are basically near most Air Force bases and NASA centers. We have a small contingency that reside there because they'll be supporting specific projects. We also have people at Vandenberg Air Force Base as well as Cape Canaveral because of the launches. So we have, again, sort of all over the place, but that's why the math doesn't quite add up. In terms of the leveraging of our cross-disciplines, wanted to, it is not showing up well. I am so sorry how that happened. Again, we have, I will let you know, these are bachelors, this is masters, and then this is PhDs. So we have approximately 700 PhDs within the corporation. Basically, 75% of the people have advanced degrees. We do have bachelors, of course. And then all of my names, I did not notice this earlier, sorry, did not come through. Basically, we have an assortment of engineers, all sorts, civil, commercial. We have physicists. Optics tends to get stuck a little bit in the other because they didn't know how to characterize us at the beginning. So now they're learning. So we're going to be, having our own categories. But again, it's a broad range of engineering disciplines that we hire. So again, goal is to have creative problem solvers with strong technical skills, and then we do solve really kind of cool problems. So it's really nice to work there. So fortunately, this did not get problems rendering. So you will see the types of engineers and the types of work that we do within the engineering technology group. And again, sort of here you go, optical sensors down at the bottom. This is my division where I am, and then this is my department. And so again, you see a lot of different types of disciplines, different questions we're answering, the concerns we have that the customer needs us to be able to adequately state that things are good to go for launch, basically. And then in summary, I covered a bunch of the challenges and processes associated with designing, building, and deploying EO systems. And then we talked about trends in the aerospace industry, which is concurrent engineering, and then smaller platforms, whether they are CubeSats or airborne sensors, to develop future space technology, and then discussed a little bit about what it's like to work at an FFRDC and the research opportunities there. So, thank you.